Good morning, everyone, and welcome to our fabulous day of programming for Earth Science Week 2024. We're really super excited. It's a fabulous program that we've got aligned for you today. Sessions pretty much every hour. Please put in the chat where you are coming from across Australia. We're very excited that for all of our programs for today, we have people from every state and territory across Australia. So no matter where you are coming from, hello and good morning, and thank you for joining us. What we are going to do is our first session is actually from Geoscience Australia, and Geoscience Australia is supporting and funding this entire event for Earth Science Week. So very excited and thankful for enabling all of these programs to be delivered for free for all of you today. Please remember, if you are registered for any of the other sessions as well and you can't make it, you will get a copy of the recording as well. So if there's things that you've missed and you want to hear again, please let us know. I love that we've got years 5, 6M, the best class. So that's good to know. Wonderful. So I am going to introduce you to Tamara from Geoscience Australia, who's presenting our fabulous session this morning. Hello, Tamara. We'll be keeping an eye on the chat as well. So Tamara's got questions for you. Put your responses in the chat. And if you've got questions for Tamara throughout the program or at the end, please put it in the Q&A. So thank you so much, Tamara, and to Geoscience Australia for kicking off our fabulous program today for Earth Science Week.
Hello, everyone. So excited to celebrate Earth Science Week with you all today. So as already mentioned, I'm Tamara, and I've also got the wonderful Emily as per my sort of rock and hand assistant today. So you'll be seeing her helping me with some of the work today. And we're both from the education and outreach team here at Geoscience Australia. So we're joining you today from the lands of the Ngunnawal people here in Canberra. And science has been done on this country and all country across Australia for thousands and thousands of years. So we just want to pay respects to elders past and present and acknowledge any Torres Strait Islander or Aboriginal people here joining us for this session today. Now, we're going to have a bit of fun today and be some earth scientists. And how we're going to do that is we're going to learn about some meaningful minerals and some resourceful rocks. There will be several activities throughout the session, so it's really important that you tune in, you engage and give it a go. If you're in a classroom, you can share with your neighbour or have a chat about your answers. If you're by yourself or in a smaller group, you can either work together and write out, or you can add it to the chat and we'll be able to track that information. Also, as already mentioned, if you've got any of those burning questions as we go through, you can add them to the Q&A and we'll get to that before the end of the session. So let's jump in. Now, in the crowd, do you collect rocks or have a rock collection at home? Feel free to add it into the chat if you do. But when I go out in nature, I really enjoy looking for new rocks I haven't seen before. And I always wonder what stories they could tell. How did it get here? What is it made of? And who else might have seen this rock before I saw it? Today, we're going to learn some stories about rocks and about how they can be used as a really important resource. Now, we know that rocks are part of our natural environment. They're a key part of our landscapes. They're part of our mountains, our coastlines, and our deserts. Now, we have a lot of really special places around Australia that highlight these amazing rocks. So do you recognise any of these famous rocky landscapes from across Australia? I'm going to give you 30 seconds now to have a think and see if you can name as many of these as you can. And then we'll come back when the timer is done. So you're tracking the timer on the middle of my slides. And that's starting now.
We've got lots of suggestions coming through.
That's wonderful to hear. We've still got plenty of time.
Lots of people have multiple ones as well.
I was hoping these would be ones you might recognize from around here. Alrighty, it looks like time is up. So Karen, do we have a couple already suggested?
Yes, so we have Jet has noticed the Three Sisters.
Very good. Yep. So the Three Sisters from the Blue Mountains. Very good.
And many people had got that one right. Maddie's got the mentioned the Blue Mountains that she's noticed there as well. Rich has said Uluru.
Very good. Yep. Very famous one in Australia.
Yep. Where else are we? Let's just keep having a look. Oh, mostly just the Three Sisters and Uluru, and some people are saying Mount Wellington.
Good job. Yeah, so there's a couple really tricky ones in here as well. But yeah, let's run through each of them so we all know the answers now. So yes, absolutely. That first one is Uluru from Northern Territory. This one's a little trickier. So this is the Babinda Boulders. So this is north of Innisfail in Queensland. So we've got, if anyone's from Queensland, it's a bit more of a famous place where there's a beautiful river and you can see these amazing boulders sort of along it. We have got the Three Sisters, so the Blue Mountains in New South Wales. So very good guessing there. This one is actually called the Remarkable Rocks. So this is in Kangaroo Island near South Australia. So some really amazing rock formations through that area. And yes, definitely we have our Mount Wellington, and it's also called Kunani. And so this is in Tasmania. So we're going to investigate a bit further into some of the rocks that make up these famous landscapes. And we're starting off with this rock here. So we're going to look closely at rock 1, which is our sandstone. And we're also going to have a look at our second rock, which is a granite. And in a moment, we're going to describe what we can see in each of these rocks. Now, it's okay if you're not getting a super quick answer as to what you can observe, because we're going to have some pictures in the slides to remind you for our activity. Okay, so we're going to be looking at these rocks, and I want you to describe what you can see. And what you're seeing is some of the properties in these rocks. We've got a couple hints at the bottom there. So for colors, is it sparkly or dull, or some patterns you might observe? But I want you to try to describe as many things as you can see for each rock, or you could focus on just one for the next minute. So again, we're going to have our timer set up for you to have a go. So starting now. Alrighty, it looks like time is up. So let's see what answers we may have got. Did we have anything in the chat, Karen? If not, I'm happy to talk through what I can see.
Yes, we've got the right is sparkly with the lines through the middle, combination of colors. Someone else is saying about the brown layers of the sandstone. It's made up of the grains of sand particles of brown and orange. We've got some really detailed responses, everyone.
That's wonderful.
Looking at different patterns and shape, different layers. Wow.
That's so good. And that's exactly it. When we're talking about these rocks and minerals, it's all about the different patterns and textures we can see. It's the colors, it's whether it's sparkly or dull. It's all those different features we can see. So perfect. And so that these are two rocks, but they have very different properties when we look at them. And we're going to look at another rock. And this one is a less common rock from Australia. This is called a chert. It's sometimes named flint in other countries, and it also can be nicknamed red jasper in this particular version of it. And so we're going to have a bit of a closer look at that one as well. And so if you've ever played the game Minecraft, this chert is the closest we have to redstone in the real world. But it doesn't conduct electricity like in the game. It doesn't have the same properties in the game as it does in the real world. Instead, the chert has a very important property that you can't see. And it's only once you go to break the rock do you see this property. And we're going to be able to have a look at that in just a moment. So when we break rocks, they can break in many different ways. And when we break a chert, it makes this sort of conchoidal fracture, which is a fancy word to describe how it breaks. And we can demonstrate that through this video here. So the idea being that when we hit certain rocks, they will break off pieces or flake off pieces. And what's left behind is a sharp edge on that bigger piece of rock. And because of that property, cherts are often used to make sharp tools or sharp-edged sort of objects. So First Nations people have been classifying rocks by their properties and figuring out their uses all across Australia for tens of thousands of years. And as we've already mentioned, that chert is a really good tool to be used as a sharp-edged stone tool. Now, this is still being used to this day, but if there's any evidence of these from the past, they are cold stone artifacts. So there's some examples there in the picture. Not all of them are cherts, but it shows you just how many different types of rocks can be used either to make the sharp edge or as that hammering tool to sort of flake off the pieces from it. Another really important example is quartzite. So quartzite has a really key property that's not one we can see, but we can feel. So when you run your hand over a quartzite, it feels really rough and it's a very hard rock. So it's actually been used as a grinding stone, and specifically the lower part of a grinding stone. And you'd have another rock on top, and the idea is that you'd put whatever you're trying to grind in between the two things, and it would end up being maybe some berries or seeds or some insects, and you'd grind it in between to see that effect and make that material. Now, another way we can classify rocks is by describing how they form. And there's sort of three broad categories we describe them as. The first one is igneous, which is where you have magma or lava cooling to make a rock. We have sedimentary. So this is where there's all these smaller pieces stuck together, like smaller rocks or shells or sands, and all those smaller pieces are called sediments. So it makes a sedimentary rock. And the last type is metamorphic. And this is when a rock has undergone some change. That could be from high heat and high pressure to make the rocks different. And out of the rocks we've seen so far today, they each will fit into these different categories. So the granite is an igneous rock, so it's from that cooled magma. Out of sedimentary rocks, we have both the chert and the sandstone, both fit in that category. And the quartzite is actually a metamorphic rock. So originally it was a sandstone-like rock that got changed due to that heat and pressure. Now, we've talked a lot about rocks so far today, but we want to zoom in even further and we want to look closer at what makes up rocks. So, for example, we have a rock here that's called a pegmatite. It's basically like a coarse granite, and it's also an igneous rock too. So having a look, how many different things can you see in this rock? So having a good look right now. How many different things? So you're going to have 30 seconds to lock in your answer starting now. Alrighty, team. I hope you've all got your guesses either written down or put through.
Yeah, we've got 3, 4, 5. Some people are saying. Grace and Charlie saw 5 as well, but there's people saying they've seen crystals.
That's exactly it. Yeah, so this is a tricky one because sometimes in rocks, there's some extra colors or textures that might make it a little confusing, whether it's something different or whether it's the same material being made out of it. So in this case, when we're having a look, this rock is made up of 3 different things, and those things are called minerals. So minerals have a fixed structure, and we can identify them through their colors or shapes or textures, but also a lot of other properties. So let's go through so that we can help identify which ones were matching up and which ones were a bit of a tricky part of the rock. So the first bit is the mica. So that's that browny, blacky, shiny sort of mineral in the rock. So that's a big chunk right at the top there. The second one was feldspar. Now this is the one that tricks people because feldspar can be many colors. In this rock, it's mostly a creamy white and it's sort of dull looking, but there's a couple little orangey bits on it. Sometimes it can be pinky colors, sometimes it can be greeny colors. So it can be really tricky to identify feldspar because color isn't always the best judgment for it. But lastly, the other key one is quartz. So that's that gray glassy looking mineral in there. And a good way to think about rocks and how minerals make them up is to picture it like a cake. So in this case, the rock would act like the cake, and all the minerals are like the different ingredients we use to make the cake. So depending on which types of ingredients you have, you're going to make a different flavor of cake. In this case, we might be making a chocolate cake, whereas if you had a different set of ingredients, you'd make a different type of cake. And it's the exact same thing for the rocks. If you have a different combination of minerals, you're going to make a different type of rock. And if we zoom in even further, and we're looking into what makes up the minerals, they're made from elements. And so, for example, that quartz we were just looking at before, that is made from silicon and oxygen combining together. So for many of the materials we use in our everyday lives, we need the minerals, all the elements inside of them, to be able to make all of our important everyday objects. So we have a really key mineral here that we use a lot, which is called graphite. And that's because it has a really important hidden property that is around hardness. So let's have a closer look now. So we can test the hardness of any mineral by scratching its surface with different materials. So by scratching with the fingernail here, we're going to see that there's a bit of powder left behind. So that means that in this case, the fingernail is actually tougher or harder than that graphite. If we do the same test, say, on that bit of quartz, and we're trying to see if any bits are coming off, we're not seeing any white powder. That's still just that black powder left behind from the graphite. So in this case, the quartz is actually way harder than the graphite. So because graphite has a really low hardness, we actually can draw with it on paper. If we try to do the same thing with the quartz, we don't see anything coming off. So between those two minerals, if we were trying to choose which one to make a pencil out of, it's not going to be very good trying to use a quartz one. You're never going to be able to draw anything. But if we have a closer look at our pencil, we can see that that is actually graphite right there in there. And that's how we're able to draw so many amazing things with our pencils that you probably use in your classroom or maybe in a drawing class. So we're going to look even further into what minerals properties they have, how we use them in our everyday lives. And we're going to do that by doing a mineral matching game. So I'll hide myself so you can see the full table, but we're going to match each of the objects from our everyday lives to the minerals or the elements inside of them that are needed to make each object. Again, you're going to have a minute to match up each one. If you're talking to your neighbor, you can just discuss. If you're typing in the chat, we've got the numbers for the objects and letters for the minerals to help make it easier to tell us which ones you think go with each other. So we're going to start that minute timer starting now. Alrighty, team, let's find out the answers. So I'll hide myself again so you can see the answers, but I just wanted to let you know I am here in the background. And let's run through. So I know we've probably had a few answers put in the chat. Let's go through it all together. So the first one we're going to talk about is the hematite. So that's the first mineral on our list. And that contains iron, which can also be turned into steel. And that's used to make a bunch of materials like a hammer, our nails, even screws and other materials like that. The spodumene contains lithium, and that's really important to make batteries. So this could be regular batteries you use in your home, but it's really important for when we're talking about electric vehicles and the batteries used to run them. The malachite is actually the mineral we get copper from. And so copper is used for electric wires because the copper metal can be stretched out into really thin wire pieces, and it also conducts electricity, which is really important. And lastly, the gypsum is really important for making plasterboard. And there's another name for plasterboard called gyprock. So there's a little hint there in the name, so that was a bit of a cheeky one. So we can see that many of the rocks and minerals that you've seen today are used to build our modern homes. So we can see some examples of this in a partially built home, where you're sort of seeing the behind the scenes before everything's finalized. That iron and the steel that comes from hematite is used for the framing of the house, as well as for the nails and the screws to hold it all together. The gypsum is used to make the walls, as we've already talked about. And one you may not have thought about, but if we melt really pure quartz sand in very high temperatures, it's how we make glass. And that's really important to make things like windows. If we look at a kitchen, we can see even more examples. So here we can see that copper being used for all the electricals, for our lights and our appliances. And even the benchtop or some splashbacks in some kitchen spaces will use rocks as the key material. So this could be done with the quartzite or the granite samples we showed earlier. And this is really crucial for when we're talking about what makes up our modern homes. But minerals are also needed for all our modern technologies. So you can see here on our Meaning for Minerals poster that we can trace each mineral to the key uses across a wide range of industries, but also they're a really key part of pretty much everything we use in our everyday lives. So if you are curious and you want to learn more about rocks and minerals, you can check out our range of free resources on our website at ga.gov.au/education. And this includes everything from more posters like our Geology of Minecraft poster, a bunch of videos talking about different rock and mineral properties, and even our virtual exhibits to dive deeper into the uses of these different things. But we're coming shortly towards the end of our visit, but now it's time to do some question time. So any of the questions that have been burning in your brain throughout, add it to the Q&A, and we'll jump across and do that now. So do we have anything already there, Karen?
Yes, we do. Someone was asking about when you were showing the red rock, is asking about ruby, because rubies are also red, and was wondering if ruby's classified as a gemstone. and what the difference is?
That's a great question. Yeah, a lot of people get confused because there's gemstone names for some materials, but gemstones are also representing minerals. So ruby is the gemstone name. However, the mineral name is actually called corundum. And so corundum represents a couple different types of gemstones. So anything that's pinky and red is a ruby. Anything that's blue or yellow or green in color, we actually call sapphire. So they've got two different gemstone names, but they're actually the same mineral. And that happens a lot when you learn a bit more about minerals. Great question.
Excellent. So let's have a look to see where everything else was, because a few of them have hidden back in the chat. So if you have put a question previously in the chat, just pop it in again so it's popping up, or even better, put it in the Q&A for us. Here we go. We've got Anthony's asking, how did Uluru form?
Oh, that's a good question. So Uluru is an interesting one. Uluru is basically made out of a sort of sedimentary rock. And what's happened is a process called weathering and erosion. So what that means is weathering is when you have the weather or nature sort of making things break down over time, so wind and rain. And erosion is when things move away from that point, so blown away or washed away. So at one point, it would have been the same level all across, and different parts would have been washed away, weathered away over time to leave behind the rock that is a bit more tougher than the rest of that other material. So you see this in a lot of places, that if there is a harder rock than the rest of the stuff around it, everything will eventually weather away and it will leave behind something that just looks like a random boulder or a big mountain sort of left behind. That can happen in some places. Yeah, so that's more how Uluru formed in this case.
Excellent.
Yeah, great question.
Thank you. We've got another question here. Is gold a gemstone?
Great question. Gold is a really interesting one. So gold is both an element and it's also sometimes treated like a mineral, because a lot of these other materials, like for example, that iron is an element in the mineral hematite, because we can't just find native iron metal in the ground. It doesn't exist in that form. Whereas gold actually exists exactly as it is, and we mine gold directly from rocks in its pure natural form. We don't need to pull out elements from it. So it's kind of an awkward one to classify, but yeah, I would say it's kind of like an element and a mineral sorter at the same time. But when we're actually using gold for other purposes, we describe it as an element. That's a really good one.
Excellent. So we've got another one here, kind of asking what the biology name of amethyst, but I think they kind of mean what, maybe the scientific name of amethyst, or maybe what it's made of.
Absolutely. So yeah, so amethyst is basically just quartz. So quartz is the mineral name, but the sort of gemstone name is describing the color of quartz you have. If you have a clear quartz crystal, then it's just called quartz. If it's purple in color, you call it amethyst. If it's a pinky color, you call it rose quartz. And if it's more of a browny, blacky sort of color, you might call it smoky quartz, or anything yellowy orange is called citrine. So there's lots of different names for different colors, because before we could figure out exactly what all these things were made of, before we could look deeper and see those elements, we just saw them as different colors. So a lot of gemstone names describe it by a color or a property that looks different. And then later we've been able to classify them all under the same type of mineral category. So yeah, a really good question for that one.
Excellent. We've got a couple here asking, one is, are diamonds mineral or gemstones? And another question linked to that is, where do you get diamonds from?
Great question. So yes, in this case, a diamond is both the gemstone name and the mineral name for the same thing. So that's one where it matches up. So diamonds have to form really, really deep in the earth, because it's basically if you take a whole bunch of the element carbon and you put so much pressure on it that it all connects together to make this really strong, tightly connected system of bonds. What that means is that it makes a really strong diamond. But the problem is, if something forms very deep in the earth, it's hard for it to then be at the surface where we want to get to them. So what has to happen is that they're often transported from deep in the earth through a volcanic chamber where the lava will push it up to the surface and we're able to get it exposed. So when you talk about diamonds, they're often found in what we call diamond ore or kimberlites, which is the rock that contains all the other volcanic bits that got caught up with it and the actual diamond itself. So yeah, so there's really cool places in Western Australia that is the Kimberleys, has the kimberlites and the diamonds. So there's a lot of connections to how things are named from where they're from. Yeah.
Excellent. So we've got a question about mountains. One specifically, Peter's asking how Mount Wellington formed, and then someone else was asking in general, how do mountains form? So maybe we can combine that one.
Yeah, sure, absolutely. So when we sort of talk about different mountains, it depends on, there's kind of two main mechanisms in this context. So Mount Wellington, if we're from that picture, it actually had a whole bunch of little black sort of tubes or columns, it looked like on the image. And what that represents is actually, it's a volcanic rock. So it's a whole bunch of chains of little bits of volcanic rock that were sort of formed there. So Mount Wellington is actually kind of built from a volcanic sort of incident that's created it. More generally, when we talk about mountain building is when you have, it's a bit of a step back, but basically our whole Earth is made up of different layers. The outermost layer of the Earth is called the crust. And the crust is broken up into these smaller pieces that are able to move around and interact with each other, and they're called tectonic plates. But basically, when these pieces are moving around, sometimes they're going to collide with each other. And if you've got two pieces of plate that are both land pieces, so it's got that kind of rocks on it, when they come together, they're going to push together and smoosh together and build up and make a mountain. So some mountains are formed from this process of smooshing together rocks and folding up. Some mountains are created by weathering and erosion where it looks like a mountain because everything else has gone away from it. And other ones are sort of left behind parts, so of like volcanic systems. So you can kind of get a couple different interactions of how we describe mountains. Yeah.
Fabulous. Okay, we had one over here, a couple ones about the most valuable mineral, and have we found new minerals on meteorites?
Oh, okay, very good questions. It's really hard to say what the most valuable one is because value has two different purposes when we talk about minerals or gemstones. There's the rarity of something, which makes it more valuable, or there's the fact that it just looks really pretty. So for example, as we said before with quartz, amethyst is the exact same as quartz, it's just purple. But that makes it more valuable because it looks cooler than just clear quartz. So that's why it's really hard to judge value on things. I think one of the ones that's very valuable from Australia as a good example is our opals. So opals are basically, if you picture it really, really small, if you were to look inside of that, there's kind of like a quartz-like system, but there's a system in there that allows when light hits it, it gives like a little reflection. It's like little bits of water almost built into its chemistry. So I've got actually a little example of opal here today. We can swap across and maybe show that here. So these are a couple smaller pieces of opal. You can see that comes in lots of different colors and even the rainbow effect when the light hits it. So this is our national gemstone. So I'd say this is pretty valuable as a good example from Australia for that question. So a really good one there, team. In terms of meteorites, so there's a couple different types of meteorites that we'll explore. There are ones that are like stony or rocky, where it's as if, like, for example, a piece of the moon, if that hit and landed here, that would be more rocky kind of meteorite. We have ones that are iron and nickel based, so they're basically a big chunk of metal. And there's ones in between where it's called like a stony iron, where it looks almost a little bit like a stained glass window. We've got bits of metal and little crystals inside. A lot of these have similar materials to what we have on Earth, but there probably has been a couple new minerals discovered for that process, or just unexpected things. So different amounts of elements maybe inside the minerals, different to what we have on our planet. So there's still lots of research going on, because every time a new meteorite lands, we get to learn a bit more. And as our technology gets better, we get to also see further into space and learn more. So yeah, really solid question.
Fabulous. We've also got another question here about how high does the temperature have to be to make glass?
Oh, that's a good one. I should know this off the top of my head, because a few years back we did a whole lot of work around natural glass and how it works. We actually, one of the virtual exhibits we do have on our website is all around how natural glass and man-made glass forms. So I highly recommend checking that out afterwards, just to make sure I'm accurate. But basically, when we make glass ourselves, we take the quartz and we add in a couple of other ingredients that help bring down the temperature. Because if you're just trying to melt quartz, it's very, very difficult. You'd need really, really extreme high temperatures. So we add in a couple of other extra bits of chemistry in there that it brings down the melting point to make it easier for us to make it. But if you've ever seen a glass making video, they have those big giant thermoses and they have to let it slowly heat up and melt that glass. At least, I think it takes about 24 hours to do it. So once it's all molten, you can do your glass work, you can make windows, you can do whatever you want with it. But that initial process does take a bit of time, and it definitely takes a lot of temperature. So yeah, definitely check out our exhibit. It will have the exact number there, and it will talk you through not only how we make glass, but also the different examples of natural glass that happen in nature. Really good question.
Awesome. There's another follow-up about opals. So there's a few questions about opals, which I think you've covered, but and Anthony wants to know why opals are different colors.
Great question. Yeah, I can explain that a little better. I kind of skirted over that before. Basically, right into its chemical structure, the simplest way to picture it is if you took a bunch of quartz and you shoved in between all those sort of bonds some water into there. And it does the same sort of property that if you shine light on water, and sometimes you get little water droplets, you get the rainbow effect. That's basically what's happening in a sort of chemical way. So it's a really weird way to think about it, because it's sort of built into the chemical structure, but we're basically seeing that same property of rainbow effect. When light hits water, it's able to separate out into the different colors. And that's why opals will give off these different rainbow effects, especially if you turn it and twist it around. So there's a couple different minerals that have it built into their structure, or it's just a part of how light, when it reacts with things, it causes it to give us a different color effect. Yeah, that's a really good question.
Fabulous. Well, we're going to stick with water for a moment. How does water carve cliffs?
Oh, good one. So what you need to picture is that when we're talking about that sort of weathering and that water carving into things, it's over a very, very long time scale. So we're talking not thousands of years, we're talking millions to billions of years. So we've actually been able to demonstrate that even in our own exhibits here at Geoscience Australia, where we have an experiment where you drop some water on a rock. And even over just 1 year, we've seen several holes form in that rock or other things happening as more and more kids go and do that experiment. So what's basically happening is that every time that the water brushes across that rock, it might take off a tiny little microscopic bit. But if that keeps happening over years and years and millions of years, you eventually start carving out a lot of things there. There's also a couple of other properties that can happen. For example, if you're in a very cold place, maybe there's also some ice. The water will flow through, maybe get into a crack and might crack it open more. So there's kind of a combined effect of multiple things that will slowly eat away at rocks to sort of shape them into what they are. And you can, if you zoom in into Uluru, you can see channels along the rock where when it's been a large rainfall, and you can see where the water has sort of flown. And if it sort of carves out a path, it will continue to carve out the same path, because it's much easier to water to flow along a groove that already exists than to try to make a new one every time. So yeah, you get this sort of continual eating away. Yeah.
I've got a tricky question and an easy question to finish up
Okay.
with. So Sally's interested to know how the oxygen and silica merge to make quartz.
Great question. Yeah, and this is something that as you go through more of your science through school, you'll get to learn a bit more about it. But basically what's happening is when we talk about the elements in minerals, they are connected and sort of bonded together. So when we talk about quartz, quartz has got one little silicon sitting in the middle and there's a bunch of oxygens connected to it. And then multiple sets of that happen over and over again till you make the whole big crystal. So you get these kind of little micro patterns when you look at a little part of that mineral, and then picture it multiplying all over the place to make that. And the different ways things connect up will give you different properties we can see. So quartz is quite tough. It's a really hard mineral, and that's because it's really strongly bonded together. Whereas graphite and how it's made out of carbon, it's kind of made in little sheet patterns. So it's easier to break off a certain layer off of it. So a lot of that comes through their properties. But yeah, if you're really curious, we do also have an exhibit around identifying minerals. And it actually is really good at talking through why they have certain properties and where that comes from. So that's called Identifying Minerals as a virtual exhibit on our page as well. Yeah, nice.
With the recording, I'll send some of these links as well in there.
Fantastic.
So you can follow up on all of these. And Dominic would like to know what your favourite mineral is.
Oh, thank you for asking, Dominic. I have got a really wonderful one to show you today. So we'll put it under the camera here. This one is my favorite because it's called labradorite. And this is actually originally from Canada, where it originally was first found. My favorite property of this rock is that it's called iridescence. So as we're twirling it in the camera, you can see that there's different colors or different shine coming through. And this is actually the same or similar basic mineral as what we saw before, which was that feldspar. But this one has that special property where when the light hits it, different angles will allow different things to sort of shine through. So it's a little similar to how the opal, when you shine light, it will change colors. But in this case, it's just about how the layers of it built up means that when the light hits it, it bends and changes on the different angles. The other reason I really like this one is that it's a pretty common mineral, being a type of feldspar, which is really common. And there's even lots of Australian examples as well. So this is a really good one to add to your collection as it's not too expensive, but it's a really fun, beautiful colors in it.
And that is one of my favorite ones too. I love being able to shine it, especially outside in the light. Well, thank you all so much for joining us today. What amazing questions. And apologies if we didn't get through to all of your questions. When we do send our follow-up resources, you might be able to have your questions answered there, but you can also email any follow-up questions as well, and we'll do our best to answer them then. So thank you so much to Tamara. And again, thank you again to Geoscience Australia for supporting these wonderful programs for Earth Science Week. It is a great way to start off learning so much about our rocks and minerals. And our next session is the rock cycle, which will be starting at 11 o'clock. So thank you very much, everyone, and hopefully we'll see you very shortly. Bye, everyone.